Hey there, Calc folks, back here with another what I hope is a quick little video where I'm going to do a Mathematica demo for you with some multivariable function work here, folks. I want to get you started with that in this chapter. Visualizing multivariable functions is not easy. This is going to help us out in a lot of different ways in working with these and interpreting these values. And these skills are going to be useful throughout the rest of our study here also. We're going to be making use of a lot of these skills throughout the rest of the semester. So I want to introduce you to some of that now and build on all of this. And I have been hopefully doing that with the demos up to this point. You've been getting in there and playing around and being able to figure out how to work within Mathematica. I guess there is probably a starting spot somewhere, but I've just kind of dropped you on the trail here in some regards, showing you a little introductory stuff, but we're out there just exploring. And I'll tell you, I'm learning new stuff every day too. I may have to pause these videos and go look at something real quick just to figure out a line of code if I don't have things right. As with any computer program, it can get buggy if you just miss a little symbol in there or don't spell something correctly. It'll certainly bug out on you. So you got to be really cautious with regards to all of that. It's not forgiving in any way with respect to syntax and command usage. So, if I run into those issues, I'll pause the video real quick and see if I can't figure out what's going on there. But what we're just going to look at today, if we bring over the Mathematica, I do have the title up there. Plotting multivariable functions z equal to f of x comma y, and doing a little bit of domain analysis. Right, that is my plan. I have gone ahead and highlighted the cell, my entry cell for you here, folks, so you can recognize it. And I've actually done an Alt 8 on it. An Alt 8 on that cell will make it into a bit of a command cell for you, and it'll actually automatically highlight things for you. It'll automatically highlight your code cell. We're going to want to put in a function of x and y, a multivariable function. And a lot like single variable functions in Mathematica, you are going to declare them very similarly. Right, you're going to give them a name. I'm going to call this one little f, right? We're going to work with little f here. It's going to have an independent variable of x, it's going to have an independent variable of y, and it's going to represent our z value, right? And recall, this is how Mathematica takes as entry, allows a user-defined function in this manner, where I'm going to say that this equals, now notice it's going, okay, he's making a function, or the user is making a function here, right? Let's look at a function I think have looked at in our work. Square root of 36 minus 9x squared plus 4y squared. This has some interesting stuff going on in it, in its analysis. Now, that will be the function that we are working with, and certainly we can double check and just go ahead and run that, and Mathematica will show you what function we are looking at. And certainly that does align with what I'm thinking, right? Where we might want to consider coming along and plotting this function, taking a look at what it looks like in three-dimensional space. That is plotting multivariable functions. One of the easiest ways to go about plotting a function is to use the command plot3d and apply it to our function f of x comma y. Now you can just state the functional behavior down here and consider plotting that point over bounds of x and bounds on y. But as I like to do, I like to build a function that I can adjust later and adjust easily, right? So I always like to declare my functions first, because then I can do all sorts of things with that without having to recall it each and every time as the square root value. So I'm going to just put that in there, f of x comma y, and declare that function. All right, and we are going to look at values of x from, we could look at negative 10 to 10. We could look at y over bounds from negative 10 to 10. Right. Hit enter, and we will get a nice little graph of that function. All right. That will illustrate our function here. Now, certainly it hasn't laid out any of the axes, and I will point out it's not quite in scale. Notice the scale here, right? If this is from 0 to 10, this is from 0 to 20. It doesn't quite appear in scale. So you can adjust scale by doing aspect ratio. You could put that on automatic. It's going to automatically why didn't you automatically? Hold on. Not automatic. Let's try 1 to 1. There. No? What is the deal now? Oh, because it's not aspect ratio. Da 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 da. 3 dimensions. Aspect ratio is how you adjust scale in 2-dimensional space. It's box ratios. It's box ratios in 3 dimensions. You could call them out as a set where the box maintains a ratio of 1 to 1 to 1, or you can adjust the ratios here. It looks like it's about 1 to 1 to 2, or 1 to 1 to 1/2, depending on how that would work out. Not quite certain on Mathematica, but automatic. I like automatic. Automatic does kind of give us a nice, quick, scaled illustration. Sometimes, however, the scale is too much. Right? You can always leave it blank, and Mathematica will do its best to fit it in. You can set your box ratios to 1, 1, 1. Right? That gives you a nice standard-looking box size, but realize things will not be in scale. Or if you want things in scale, automatic will place your illustration in scale. So there, our plot is in scale. If we want to add one more line of command here, the next thing we might just add is simply axis label. We're going to label our axes. X-axis we'll label X. Y-axis, the other horizontal axis, we'll label Y. And then the vertical axis we'll label Z in value. And that should label our axes. All right. Excuse me. Now that's one way to graph in Mathematica, to plot a surface. I will tell you at times that it sometimes fails. Sometimes doesn't do the best job. Let me show you another way to plot, though. Sometimes you'll look at the graph and you go, hey, that doesn't quite what I expected. So there is another way to look at the graph, and that's as a parametric plot, or as what's known as a parametric surface. We're going to actually make use of some parametric surfaces in Chapter 17. We're going to define parametric surfaces towards the end there. But essentially, a parametric surface is a multivariable vector valued function. Right? We're going to take the ideas of 15, mix them, or 14, mix them with these ideas here in 15, and talk about them as a vector valued function that has more than one independent parameter. Here we're going to use the parameters x and y. And we're going to make x independent, y independent, but z is going to depend upon x and y in this parametric surface. How do I do that? Well, it's going to be a 3-dimensional vector where the first dimension is x, the second dimension is y, and the third dimension is f at x comma y. Right? That will define this as a parametric surface. And again, we might look at this for values of x from -10 to 10 and values of y from -10 to 10. And one thing we might do here in a moment is we might go up here and make standardize these bounds in our code. Right, y from -10 to 10. And you will see here I get a very comparable surface. Right? And you'll notice that I believe it automatically puts that one into scale. Right? You're going to get a nice scale on this one. We don't have to adjust the scale respectively. All right. Make this a little bit more like a code. With those bounds, we're going to be adjusting them a lot here if we set up a couple more plots along the way. So our A's and our B's have been bounded between -10 and 10, and our C's and our D's have been bounded between also -10 and 10. Right? We can come down here then and replace all my bounds on X with A and B, and all my bounds on Y with C and D. And now I can just adjust them above for my illustrations, right? And it'll adjust respectively in both. All right, so that makes it a bit more codish. All right. Now, one of the reasons I do show you this, let me show you another code here, another bit of functional behavior. I'm going to actually go ahead and copy that function. I just copied it. Control X will copy. I'm going to go up here and call this g of x, y. Right? So I can store that as a practice function, and I'm going to put in another function here we're going to make use of. H of x comma y. Let's explore this function in our behavior. Let's look at x squared over x plus y. Now, one thing I will always caution you with when declaring your functions here, folks, is when declaring your functions as we do up here in these practice cases, right, we might actually start to define these as these. These are going to be our practice functions. We can go back and forth between these rather quickly if we declare those as our practice functions. These are going to be our inputs, adjustables, we'll say. These are the values. Let's spell adjust right. Right, those are the values we're going to adjust. And right now we're going to have our, down here, maybe our code. And you can see I'm just putting in a little documentation. Right, this is our program running down below. We want to try to alter that as little as possible. Now, I'm not going to guarantee that. There's certainly going to be some adjustables down below here. But what these are, maybe we should just call these out as plots of the surface z equal to f at x comma y. Let's just say it that way, right, in our documentation here, right? And folks, to document, you do have to use parenthesis star, document, end with a star, right? As long as your documentation appears between a star and a parentheses, your program will only read that as documentation. And that's a way to kind of keep track of things. Like down here, I can say these are my x bounds, whereas these are my, I always like to put the document symbols before I write my documentation so that everything doesn't shift on me in color and in format. But then those are my y bounds. Right? Now notice what I did also do here is I did change my practice function. This is what's nice about having these practice functions up above here is I can just come down here and I can switch real quickly now between G and H in my study. All right, there's the graph of H. Here's the graph of G. All right. Oh, can I get it? All right, to look respectively. Those are kind of hard to move around in space there. And the way I am moving around my graph, folks, is I am hovering over it, and you can do this on the cloud version too, clicking on it with the left click and just rotating. You can do that. Shift, if you hold shift and left click, you can actually move it back and forth in that space or up or down. Right, respectively. Alt will always take you back to the cursor because it will lock you in when you start to do that. And then if you hold control and left click, you can actually zoom in and out on your surface. Right? Now I am locked in kind of a rotation here when I dip out of that. If I hit Alt, it'll take me back to the cursor. So that's just playing around a little bit with the graphical aspect. Now both of these graphs look the same until I kind of zoom in on them. That's why I put these up here, is if we go in down to a really finer level, maybe we zoom in from -2 to 2 in both dimensions. And notice this is what's nice about having it a bit adjustable, is I can adjust those things pretty quickly here. Right? Notice the difference in my two graphs. This graph doesn't change very much in terms of the plot 3D, but the parametric plot certainly becomes a little bit more refined in its illustration. Right? It does certainly start to illustrate what we might say is some very interesting behavior at the domain value of 0, 0. Or I should say here, at the exclusion in the domain given by 0, 0. Right? As we approach that point in the xy plane, right, for x and y values in our domain, right, as we approach that location in the xy plane in two-dimensional space, right, there's some interesting behavior here that you can start to see actually a little bit more refined in this graph. And what I can do to actually make these graphs bigger, what sometimes works as a nice command is image size. You can adjust the image sizes. And I realize you can't read that. Let me come up. You can do image size, and actually you can move these to the next line too. A couple of image sizes. You can do large, small, medium, or full. Full will use as much screen as it can to illustrate that space. Medium is also not a bad size, right? And notice I have zoomed in some there, so I can zoom out a little bit. Maybe down here I should set this image size also to medium. It looked like it defaulted over to that once I changed the 1. Okay. But you can definitely see there's some different behavior going on in these two graphs. Both graph very similarly. Right? I did have to automate these box plots where I haven't had to do that here in the parametric plot. Right? But, you know, sometimes the parametric plot does give you a bit more of a refined surface, right, when looking at the plots. Right? And then likewise up here you can play with the different practice functions. Right? We can put in another function here. We can maybe define j of x underscore comma y underscore. Why not I? Well, because I is imaginary in Mathematica. So we can't call out a function as I. What do we want to call here? What's another one we sometimes see? Common one here. We got that, we got that. What am I thinking? We've had another one, haven't we? X squared over y squared. Oh, yes, yeah. I remember which one now. Wasn't it no, it was 1 over, what was it? Oh, gosh, I can't remember. But we would be able to call out another function here if necessary, another practice function. I'm not going to waste our time thinking about that at the moment. It'll come to me. It will certainly come to me. Right? But you could put in practice functions there and do this analysis by just changing around this value. Right? Here's this curve here just over that domain region, right? Respectively. You could adjust out your domain region if you wanted to look at more or less values along a particular axis, right? Respectively. Now, let's go a little further into domain. Let's keep this up at the top here. Let's look at doing a bit of a domain analysis. Right? Now, the first bit of the domain analysis really does require you to recognize what are your domain limitations. What I might call these out as an adjustable. I might call this out as our constraint. Right? And if we're looking at g of x, what is our constraint? Is this value inside of the argument here, 36 minus 9x squared plus 4y squared. That constraint has to be greater than or equal to 0. So I can make that, right, a statement in my adjustable there, if I wanted to, where I could change that constraint in the case of h. In h, I could change it over to, well, x plus y is not allowed to equal 0. Now, notice how I obtain the not equals, folks. That is exclamation point equals 0. and that'll change over to a not equals. To do less than or equal to, if we go back to G, put in G, and it has to be greater than or use an equal sign, and as soon as you put in the number 0, it changes over to a greater than or equal to 0. Now make sure you are saying that is for function G. So this is the easiest way I can see of kind of making this a bit of an adjustable in here. Right, folks, without actually having to go down into the code and doing this. And the other thing we might actually call out here, you have the constraint, and then what I might call the constraint function. The constraint function is actually the function found on the left-hand side of this constraint. It's the functional behavior that has the problem without the inequality in the relationship. All right, so perhaps I'll say it this way. All right, respectively. All right. Now, in our domain analysis, one of the first things we can do is we can try to understand the region described by our constraint function as a set. Right? We often state our domain as a set. So what you can do here as a nice bit of code is we can do a reduction or do a reduce command. And we can just do a reduce command on the constraint. That is like putting this statement down inside here as our reduction. And actually, we want to perform it on the constraint. Does that work? Yeah, that works quite as expected. We can do a reduction on our constraint. And it does give us, in a sense, the set of points that would describe our domain, where all values of y in the real number system such that x is a value between these values. And this double ampersand, that is describing our, is saying the word and. Y is an element of the reals, and x is between these values, respectively. Right? That's what that domain statement is saying. One thing we do point out, it is telling us the constraints behavior in terms of variable x being independent. Right? Another way we can write these is by declaring what variable we want to be independent in the relationship, or dependent, I should say. And here we're making x dependent by declaring it for x. Notice x depends upon what y is. Y plugs into this equation and we'll tell you how x will have to behave. So x will depend upon y. Y is any real number in the real number system. You can also do the reduction statement on your constraint where you make y. Typically y is your dependent variable. So this is a little bit more classical. Right? But notice how ugly that result is. You got to be able to translate that in Mathematica. That double ampersand means and. So here y is an element of the real number system, and we have this happen. X is less than or equal to -2, and y is less than or equal to this, or, now that double absolute value or that double vertical is the word or, y is greater than or equal to this, or, right, that was all one event combining with this initial event, or with this initial event you could combine this event. X is between -2 and 2, or x is greater than 2 and y is between these results seen here. A terribly bit more complex description of what was said a little more simply with x as the dependent value seen above. I do believe when you run this reduction, Mathematica goes with the shortest description of the two seen down below, if you don't specify dependent value. I think that's what it does. I don't think it defaults to x. I think it defaults to the simplest of those two options. Right? But you can call out those two options individually as seen there. Right? Now, what does all that mean? How we can see how all that is interpreted, folks. That's where a region plot comes in handy. A region plot is going to give us a two-dimensional illustration of this domain. And the way we're going to get that region plot is we are going to run it on our constraint again. This is just like bringing this inequality down. And dropping it in to the region plot. All right? But I can change my constraint above, and it changes it in all these respective locations. So when I play with my practice functions, I can just change it above, and it makes all the changes down below. So I am going to want to look at my constraint over values. Again, now this is x from A to B, and y from C to D. And notice, again, I've declared A and B and C and D above as our bounds on x and bounds on y. So in this plot, right, it's going to have similar bounds to what we see down in our three-dimensional plots down below. And if we plot that out, what happened there? Region plot constraint. X from A to B. I'm going to have to, let's see here. Why did that fail? Oh, I know why it failed. No, I don't. Why did that fail? That should be looking at G. There's G, there's G. We're looking at our constraint. Hold on, I'm going to pause this for 2 seconds and see if I can't go over and figure this out. All right, folks, can you see my error? This is why it's called an analysis we're performing, is because you have to look at different things here. You have to analyze what's going on here in all of this. Can you see my error? Let me scroll down here. Why don't I see the domain showing up? It's not until I really look at these graphs down here that I answer my question. Remember, your domain is going to show up over your XY plane, and we have this graphing the XY plane seen in this image here. And if I roll up from above, I really don't see the domain concerns yet. And actually, we're right on the boundary of those domain concerns. You see that boundary right here, right? My x's are stuck between -2 and 2 here. All right. The boundary of 2 and -2 plays an important role in defining this region. All right. We're right on the boundaries of where we're going to start to see domain concerns, in a sense. All right. What we have to do is adjust our bounds of observation. So we might come up here and adjust our bounds back out to let's go with -6 to 6. Maybe that works. We'll adjust both of them respectively. So it wasn't much of an error of ours down below. The region plot is still going to happen on the constraint, but it was what these bounds were being set at up above, right? We weren't really over a region where we could start to illustrate any of those domain concerns. Certainly that region is still going to be described in these reductions, right? But what we were observing was not focused on that region, right, where we started to see some domain concerns. Now, if I run this code, we will see an illustration of our domain. Now, one thing to note about a region plot, folks, the region plot, well, here, it doesn't plot the boundary. Right? I could change my constraint. It's really not concerned with the boundary at all. If I was to change my constraint over to greater than 0, right? Let's say that this was 1 over the square root of 36 minus 9x squared plus 4y squared instead. And we had that be our constraint. We had to be greater than 0, right? We are going to see that constraint come out in our description here, right? X is not allowed to equal these values anymore. You'll see that'll be the one little change that happens in our domain description. But the graph is not going to illustrate that at all. Region plot only graphs over two-dimensional regions. That boundary is a one-dimensional region, and it doesn't concern itself with that one-dimensional region. Region plot can't have us graph that one-dimensional region. So you are the one who has to kind of understand that along that boundary it would either be solid or dotted. And here we would say that it would be dotted. Now, if you wanted to illustrate that, folks, you could add to this plot a two-dimensional plot, folks, of the boundary concerns. Now, where the boundary concerns would come from, right? What we want to remember is they are where your function f of x comma y, right, would have an output of 0, right? All of your boundary concerns, all of the concerns you can encounter up here as a constraint are concerned with, oh, I should be careful there. They are concerned with the constraint. And more so the constraint. This is why I had you identify the constraint function up above. They are concerned with where this function happens to equal 0. That is the exact boundary on all of our constraints up here. Either you can be greater than 0, you can be not equal to 0, or you can be greater than or equal to 0. But 0 is always the boundary. So that boundary is always going to be where the constraint function equals the value of 0. Now, how you set up an equation of equality, you do have to use a double equal sign in Mathematica. And what we're going to do with this equation is we're actually going to solve it. And it should solve it down below here for us. Now, we're getting a lot of output here. Let's go up here and turn some things off. I've already turned off F. Let's turn off G. Let's keep our input, but let's turn off the constraint functions. Let's not say those. We don't really need to say our X and Y inputs. Having one of these is useful. Let's go with just that one. Let's leave our region plot on, but let's say after that is going to be our solve there, right? And we got to take out that plot for a minute, because otherwise it's going to hit an error as it tries to plot that, right? So here's our solution down below our region plot, right? And notice where that is coming from. Oh my gosh, what did I mess up there? Oh boy, where did that come from? I'll have to get into that, because yeah, that's doing something weird to those plots down here now. It may have been that plot that we threw in there for a minute. We'll see if our next plotting fixes all of that. All right, that may throw off those values. What we might consider doing now is just turning them off. Oh, hold on. It's not going to let me turn them off. That means something is set awry. Can I turn off that one? I can't turn off that one. Can I turn off this one? I can't turn off that one. Equals solve. Now that only appeared after I turned everything off. This might be a good time to save your program. It's always a good time to save. Let's see what happens here. Still getting this odd region. It may be that automatic too, and we're right on that boundary of odd, funny behavior there. Let's go full. Still don't get much behavior there. Well, I'll have to figure all that out. That may have been the error of having that plot sitting there waiting to go. That may have brought up some of the bugginess that's happening here. And in fact, what we might be able to do... Oh, no, not that. Now everything goes awry, right? Let's get rid of this. Let's go cell. Let's delete all output. Clear it out nice. You can go up to your evaluation. You can quit your kernel. It's going to say, are you sure? Yes. Come back in. You get a nice fresh program. Let's just try to run it one more time. This happens. No. It'll ask you if you want to run all the cells. You can choose yes or no. I just usually choose no. And I'm still getting the bugginess. So I'm not going to worry about it too much right now. We'll come back and try to fix that later. But you notice I did get the solution there, folks. I did get my solution right below my region plot. This value right here. Y can either be equal to this or be equal to this, and that describes this boundary seen on this region. And really what those are is boundaries on a conic section, respectively. Right? Or, well, the conic section given by a hyperbolic curve, respectively. All right? So what we can do there with that... we can, here comes the ice cream man in my neighborhood, if you can hear that music. Boy, these things are shot on the fly, folks, I'll tell you that. Let's see here. So that's our solve. You can see how that appears, but notice how that appears, folks. It doesn't say y equals this or y equals that. This is how Mathematica kind of works, folks. It puts in this arrow and says y can be replaced with this value. And y can be replaced with this value in our solution. Right? And it presents it as the set of solutions that are the set that do this material, which really means that I can use a command known as the replace with command, where I can take the values of that solution and replace them into, take them and place them into as a replacement for some other value in some other equation or expression. And all I'm going to do is place these solutions into the expression y. And what that's going to do is take what y can be replaced with and replace it with what it's replaceable with. And that's going to present my solution set as actually a set of expressions for just x and doesn't have that arrow in there. Now the replacement symbol is a / followed by a period symbol. That is your replacement symbol. And if I run that code now and we run down and look, you can see there it removed the arrow. I got to go all the way down. You can see there it removed the arrow from the code. It's just now is a solution set of those two equations. That is what I want to plot. I want to plot those two equations. Could I run it this way? I guess I could come along. Because it's a solution set of those two equations, this is where Mathematica is nice. Mathematica can plot individual values or it can plot sets of values. So we're going to plot that set of solutions. We're going to plot it. We're going to try. I'm doing a little exploration here, folks. Never done this before, I don't think. Usually I define it as another set. But for the sake of time, I'm going to do this. Let's see if this works. Now, that should have plotted those. It did. Oh, you know why? Because plot only needs one dimension. We only need to look at x values. Here. Remember? Oh, not there. Here. Remember, these are solutions that are going to be in terms of x. If we actually want to see what we're solving again, we can bring this up. And just put that the line beforehand. Right? But now we're going to plot that from x from a to b. And remember, those were just equations of x, expressions of x. Let's plot those expressions. So there they are. That's nice. They just plotted them for us. All right. right? And what we can do is we can well, first of all, we can do with that plot and the region plot is we're going to combine the two. Maybe we call the region plot plot 0, and we call our plot of the solutions plot 1. Right? And notice I did set delay them, which is fine. I could also just turn them off. Maybe let's set delay is kind of hard to explain when to use and when not to use. So just using an equal sign works, and then turning things off at the end should also work. And then we do p null, and we can lay in p1 on top of it. That's what we see right here. All right. Except in this plot, what we might consider doing is changing the plot style slightly so we can actually see it. And in this particular case, g of x, because we move that to the denominator, we got to go back and remember we're not allowed to equal this. And because we're not allowed to equal this, we got to change this plot style to dashed. Now, I will tell you this will likely not show up. It's just not going to be dark enough. Why aren't you running? Stalls out right there. Why is it stalling out? Oh, my directive. When I use the, I'm going to do a couple directives here. It's probably not going to show with the dashed unless we make it maybe a little darker in color. So we'll go with black there. Right? And it shows up as a dashed line in that illustration. You can always change the size of the dash. You want a thicker dash, we can make that thick. Right, in our illustration. And it shows up a little nicer. Now, you notice how personal we have to get there. We do have to get down here and change this directive value inside our plot style to dashed. You could write a little bit of if-then code that maybe runs here at the beginning. We're going to run a little if-then code here where we're going to look at a value we might call include. Right? Are we going to include this value or exclude this value? And when include is 0, which we're going to have stand for not include, we're going to set another variable in our problem. We're going to call it our, let's call it our dash style. Our dash style will be dashed. Right? Versus if we include is not equal to 0, it's going to run this alternative argument where our dash style will be equal to none in value. I think that'll work for us as an if-then statement. So it's going to check this condition. Now, this condition we're going to set up here. That's going to be another input. And we're going to tell it, don't include, right, as a value. Now, I do see an error here. Why is this coming up as not equals in there? I'm going to have to run that and see. And then down here under dash, that is where we're going to put in our dash style. And when we're asked to, when the include is not to include, it's going to put in there the term dashed. Now notice I did that down here. Put in that term dash styled. Hey. Let me actually, well, I don't want to bring that command around. Don't need to. Right? I put in dash style there. So that if then that runs initially, that if then that runs up here is going to ask, is the include 0? And 0 is going to stand for, we might put in a bit of documentation here and say when include equals 0, you're going to exclude bound. And then certainly when include equals 1, you're going to include bound. Right? So it's a switch. You can turn it on. You can turn it off by just making it 1 or 0. Right? We're going to turn ours on. Or off, sorry, off in this case because we're looking at g of x. Now, we run the code. Oh, it runs fine. Still getting this issue down here with these graphs. I'm going to have to figure that out for you, folks. But I end up with that solve here. It does plot that. I don't know what's going on here. Let's set these box ratios. Maybe that's it. Box ratios. Let's go automatic here. Oh, we can't do box ratios there. We got to do aspect ratio. And if you go automatic, it will scale things appropriately. Man, I'm still getting these bizarreness here. And it may be those bounds. Let's go out a little further. We had negative 10 to 10 there originally in our graph. It may just not be scaling right. I don't see that happening either. Full. Let's go back to automatic. Still nothing there. Other thing you can do sometimes is play around with the plot range. Let's go negative 10 to 10 on that. What draws that up? Man, I got some bugginess going on here, don't I? Well, what is up here? Negative 10 to 10. What if we change our function? Change this back to h. Is it because we're turning these off? Notice we went back to h, it worked out. Maybe it was because we turned those off initially. That could be it up here. I've noticed some bugginess at the beginning of programs, especially with putting some documentation in the first line before. And that might be what we're running into here. I don't know why. Let's go back to G, though. And it goes back to that. So it might, oh, you know what it is? We changed our function. That's why it doesn't look the same. Let's take out that one. Let's make this back to equals because we were playing around with this option. There we go. Everything should look like normal now. There we go, folks. Back to normal. You got to have all your settings set right in this program. So there was nothing wrong, thank goodness, in this program, folks. Notice this is all used in your domain analysis. Your remember, this only affects domain analysis. This is used in your domain analysis. And I will tell you, this is still going to be pretty clunky, folks. This works well when your constrained regions are nice regions, usually conic sections. This works very well with. This doesn't work well when you get outside of the conic cases. You're not looking at quadratic surfaces. It gets a little uglier than this. But this should work for most of the surfaces I think we're going to encounter in class. Right, folks? But keep in mind, this is just the beginnings. And at the very least, you're learning some commands here to be able to go some different ways with this, like the plot 3D command. Right? That's one way to plot these surfaces, and you can certainly play around with the plots of your surfaces. If you don't trust the plot 3D, there's the parametric plot. That's just another way to plot a surface. And it's actually going to be a way we plot surfaces here in Chapter 17. We're going to talk about parametric surfaces. And that's just an introduction to that. Up here is all the domain analysis stuff, which plays around with those constraint functions. And really where the bugginess gets, if you get outside of quadratic surfaces, is with the constraint function. Right. And solving that set equal to 0 can get really nasty. All right, so I will caution you in here. This may not work for everything, but it will work for some things. And it allows you, it's again, an exploration into these two functions. All right. Let's go back here. Box ratios. Automatic is usually a good setting. That keeps your scaling nice. Certainly you can make that an adjustable up above here. But we're at 50 minutes, so I don't want to go too much longer with this demo. But I would like to maybe try to show you a little level curve analysis. There is a way of dropping level curves in here. That's going to help us with the analysis of limits. So we may see some more of this domain analysis in the analysis of limits, and we're certainly going to probably, in more of our examples, be plotting some surfaces. But this is the beginning. All right? This is the beginning, folks. Let me save this. File, save, Math 271, Demo, Chapter 15, Part 1. We'll call it that for now. But it's saved, so I won't lose it like I did one of those there, folks, in the past. And this will be something I can share with you, all right, if you're looking for that demo. And likewise, maybe I will dip into the background here and just give a slow scroll. So you can always pause it at a particular point and check out the code. I'll bring down those plot styles, right? That's still in that plot. Let's bring it down so you can see the rest of it. I have turned it off as a plot with that semicolon at the end. Let's keep almost at the bottom here. Then remember, these are our two plots down here at the bottom. Right. That plots our surface as a plot 3D. This will plot our surface as a parametric surface, folks. Very easily set with the code seen above. All right. So with that said, I will publish this as soon as I can. I got more I want to show you. This is all just the start. Get you a little bit of coding there. Fun stuff. Fun stuff. So see you in the next one.